So we were looking at this notion of graphs. I went on my rant about how in science, in physics, graphs mean the y-intercept and the slope mean something, unlike in math where you just all you care about is the shape. I tried to convince you that graphs are good because they convert numerical data to visual patterns. I told you that every graph had to have a title, labeled axis, scale. On your test, and right now your test, your quest, your half quiz, half test, it's probably going to be towards the end of next week. The very last question, I'm going to give you something just like this. I'm going to give you some data and I'm going to say graph it. And where kids lose the most marks is they forget all the little things. They forget to put a scale. I'll take a mark off. They forget to label this axis, this axis. In fact, the next thing I need to do is I need to put a title. Every graph has to have a title. How about velocity versus time, which is what I'm graphing? Put a title on here, please. Okay. I think I forgot to put a title on, in which case I'm embarrassed if I did. Then we're going to analyze the line of best fit. So we drew a line, and this, Jaden, is where now all of our answers started to look different. Mine happened to go through about mine went through those. My slope was 1.2. I've done this same lesson 4 times. One other time I got a slope of 1.2. The other 2 times I got 1.18 and 1.2. You know, your ruler wiggles a bit. I'll take a range of values. But what we want to do is come up with an equation for this line. So my slope was 1.2 by going rise over run, and this is where we left off. What's the y-intercept? Well, it's right there. Mine looks like about, well, Bryce, you have the best view. I don't think I hit exactly at 3. I think there's a tiny little gap there. I'm going to call mine 3.1. Now, you could argue, how do you know it's not 3.09? How do you know it's not 3.08? The weakness with graphs, Parmjot, is they suck for decimals. They're good for visual pattern. They're terrible for getting data from, which is why we're going to go to an equation. So whatever you think your y-intercept is, write it here. So I'm going to go, my y-intercept is 0, 3.1. But then the second question I asked is, what does the y-intercept mean? Jordan, one of the themes I'm trying to get across to you is that in physics, graphs mean something. What is this y-intercept telling me? At time 0, what was my velocity? 0? Ah. This is telling me how fast I was going when I started. In fact, in Science 10, you gave that a special name. You called it the something velocity. Jaden, this y-intercept is telling me something. Hey! This is telling me VI. Can I use that for initial velocity? I think it's what you did last year, yes? Kennedy, y-intercepts now, they mean something. They'll tell us something useful. Is that okay, Jordan? At time 0, I was going 3.1. You might be 2.9 or 3.0 or 3. Whatever your y-intercept is. But you know, I can tell you, we started the timer after this car was already moving, if this is a car. Finish your yawn, ready to go? Mina part B says, what are the units of the slope? Slope is what over what? You all know this one. You've memorized this one from science, from math 10. What was it? You said it. Loud and proud, you're right. Okay, did you say over? Say yes. All of us right now, let's draw a little fraction bar over. But instead of doing the numbers, instead of going 9 over 7.5, 1.2, I'm going to do the same thing but with the units. What are the units on the y-axis? I wrote them. Read them. What are they? You're way overcomplicating this. Hey, what are the units on the y-axis?
Meters per second.
That's why I labeled it that way, Krisha. Okay? So let's write this. Meters per second. Y-axis. So I'm going to put that on the top where the rise goes. But instead of using numbers, Kennedy, I'm using units. There's a great trick I'm showing you, by the way. What are the units that we put on the x-axis? What's the run units? Seconds. So here's the question from Science 10. What was meters per second per second? You also wrote it as meters per second squared. Holy smokes, what, Batman? Y'all ready? Y'all ready? Hey! The slope is, and I was able to figure that out by still using rise over run, but McKenna doing it with the units, being a little clever. Okay. Again, what I want you to realize is slopes and y-intercepts for data tell us stuff. Now we want to get the full equation, and I stupidly forgot to leave a spot for this, so I think you all have kind of some room right here to draw a box, and I'm going to put equation of line. Okay. This next line, don't write down, because you'll do this in your head, but I'm just going to write it down so you can see where my thinking is. So don't write this next bit down. I'm going to write y equals mx plus b. That's our template. Don't write that down. But we're going to start there. Except instead of the letter y, go look at your y-axis. What are we measuring on our y-axis? What would be a good letter to use for velocity? V. So this is what you can write down. Instead of a y, put a v there. I got that right from the y-axis, right? M is the slope. All of you are going to write your slope right there. Mine is 1.2. Whatever you got. It's close to that, I think. I'm not going to put an x. What would be a good, what are we measuring on the x-axis? What would be a good unit to use for, a letter to use for time? T. Plus, and then B is the y-intercept. My y-intercept, I said, was 3.1. Whatever yours is. I will, on your test, ask you to give me the equation of the line of best fit. And that's how we do it. By going rise over run. You find the y-intercept by reading it right from the graph. Where kids also lose marks, every year I have kids that give x and y. No, pick letters that make sense, please. Is that okay, Krisha? Okay. Where it says a question, Jordan, ask. This is important. This is fundamental. I don't mind you asking, because if you have a question, other people do too. Oh, never mind. Got it?
Yeah.
Okay, that's okay. I love it when students ask questions. That makes my day. That means I can learn this better, Mr. Duick. That's what you're telling me. Where it says assignment, we're going to come back to that. Keep this handout handy, but we're going to do kind of a part 2 lesson and a couple of mini labs. Take a look at the handout that I just gave you. So often, when we are doing a lab, when we are analyzing something, actually know ahead of time the answer that we should get. And we'd like to have a mathematical way of figuring out. Guys, good? Thanks. We want to have a mathematical way to figure out how good we are. And there is. We call it error and percentage error. So often when completing a lab, we would like to know the accuracy or the validity of our results. If we have a known value, a correct value, to compare our lab results to, we can find our error and our percentage error. Error is calculated by, and this looks very, very high tech, it's not, taking the theoretical or calculated value and subtracting it from the known or accepted value, finding out how far apart they are. Except, I put some absolute value signs here. Those two vertical lines, you'll learn this year in math if you haven't already, are called absolute value. And Jaden, what that means is always give me a positive answer. Or always go bigger minus smaller. In other words, if the known value is bigger, go this number minus that number. Give me a positive answer. And the known value or the accepted value is often called the correct value. What other scientists with better instruments have proven is the value. Percentage error is the error divided by the correct or known value times 100%. This seems very confusing until I do a couple of examples. Let's jump on in. Example 1. A police officer uses a radar gun to clock a passing Ferrari at 211 kilometers per hour. However, the Ferrari's GPS actually shows that he was actually going at 199 kilometers per hour. That's the correct value. Okay? Calculate the error in the officer's measurement. What's the theoretical value? What's the measured value? What did the radar gun say? 211? What's the correct or known value? The error is going to be bigger minus smaller. $12? Yes? So this radar gun is off by 12 kilometers per hour. What I'd like to know is what percent it's off by. That's more useful. That gives us something to always compare things to. So the percent error is going to be the error of 12. Oh, you know what? How about for percent error, we go percent error equals, that's a good shorthand. It's, ready? We said it's the error divided by the correct value. What's the correct value in this question? 199. And then to make it a percent, we're going to go times 100% to make it a percent. This radar gun is off by 12 divided by 199 times 100%. I'm going to go to 2 sig figs. If I go to 2 sig figs, how would I write this? 6 would be wrong. 6.0 would be accurate to 2 sig figs, right? So 6.0%. This radar gun is off by 6%. Having said that, this guy is still probably going to have to pay a hefty ticket because even with that 6% error, he's still speeding. Okay? And in real life, radar guns are more accurate than that. Okay? Yeah. Quick like a bunny. Let's do another one. 2 people, I made up some names, Reginald and Dagmar, measure their weight in the morning by using typical bathroom scales, which are famously unreliable, especially the spring scales. If you have a digital scale, they're a little better, but an old-style spring bathroom scale are terrible. They have a huge error. So the scale reports that Reginald weighs 237 pounds, although he actually weighs 256 pounds. Dagmar's reports her weight as 117 pounds, even though she really weighs 129 pounds. Which measurement has the bigger error? Are there 2 people in this question? You know what? Let's cleverly divide our page in half. Ha! I'll call this R for Reginald, and I'll call this D for Dagmar. And the error is going to be for Reginald, the bigger number minus the smaller number. 256 minus 237. 19? What's the abbreviation for pounds? Well, nowadays, I think we're starting to abbreviate it with the pound key. It used to be LBS, which never made sense to me. How do you get an LBS from pounds? Stupid imperial system is why metric is better. I almost did this in kilograms, but I know most of you still measure weights in pounds. Oh, okay, fine. Dagmar. Oh, you know what? How about error, and let's put an R down there for Reginald. Error D for Dagmar. It's going to be bigger minus smaller. 129 take away 117. To subtract 12? Or am I wrong? Is it 12? Yeah? 12 pounds. Who has a greater error? Who has a bigger percentage error? Part B. You know what? There's two people again. Again, let's call this Reginald. Let's call this Dagmar. But this time we want to find the percentage error for Reginald. That's going to be the actual error of 19 divided by the correct value, the right value, the accepted value. Which is the correct value, the right value, the accepted value? Is the 256 the right one? And then times 100%, we get I'll go to, again to 2 sig figs, 7.4%. Is that right?
Yeah.
Okay. The percent error for Dagmar, that's going to be 12 divided by the correct, the accepted, the true value for Dagmar, which is what? 129? And then times by 100 to make it a percent. $9.3. So whose scale is more accurate? Even though, what did I say, Reginald? Even though the R scale made a bigger actual error of 19 pounds, it's more accurate as a percentage. 9.3%. Paige, you see what I meant? I said it's easier to do it than try and look at all the equations. Find out how far apart your actual value is from what you figured out, and then take that number, divide it by the actual value times 100% to make it a percentage. One more. Mr. Dewick estimates that it will cost him $7,650 to rebuild his porch. The actual cost is $9,800. Mr. Dewick was off. Thankfully, this is not a true story. Calculate the error. Well, the error is going to be the bigger number minus the smaller number. $2,150. I was out by $2,150. My percentage error $2,150 divided by the correct value, the accepted value, the actual value, which is which one? Depressingly 9,800 times 100%. Two sig figs, what would this be? 21?
21.
I think looking next door, right? That's a 9. That's going to become a 2, I think. 22% error. So this is your notes. You're not going to hand this in, but we're about to do a mini lab in calculating error. Let me just pause the video.